So the next topic is the next kind of games is zero-sum games, which the rules for which are exactly the same as for any constant sum game. It's sometimes simpler to talk about the sum being zero, but the idea is that the players have opposing interests. So what one gets is exactly what the other loses, and we have two players. That's two players, and the sum of their utilities is zero. Examples are matching pennies, rock, paper, scissors, as like artificial examples, games, and more practical. Chess is a more complicated game, but still a game. And a more practical example can be, for example, bipartisan elections. So what the one party gets is what the other party loses, of course. So exactly when you have two parties who compete. And there are many other examples, and this is both theoretically and practically important example. We can say a lot of about them in theory, and that was the first formally, organizedly studied area of constant sum of of strategic games historically, and also practically. There are some practical games which can be modeled as a constant sum, and we define the max-min, which is the value, the maximum value you can get when the other player tries to make you as bad off as possible, and that's natural to calculate because it's a win-lose game. So that every player wants to win, which can be said that every player wants to make the other player as bad as possible. Therefore, you need not just to maximize. So you need to maximize against the worst behavior of the other player. And in general, this max-min can also be defined as the safe state. So the safe option is to do the maximum against the worst possible behavior of the other player. But here it's not just a safe option, but it's actually what you expect, because as I said, the other player has a motivation to screw you over, informally speaking. And we'll see, I mean, prove that that actually is therefore something you can see in an equilibrium. So that's not only a stable thing, it's not only a safe thing, but it's also a stable thing. The safety is by definition that's for maximizing the worst case against the worst case, but the safety is something for zero-sum games. So we have a reason to define that, and we prove that the max-min, so the maximum I can get when the other player tries to make my situation as bad as possible, if you compare this to the min-max, so the minimum that the other player can get to me, the minimum that the other player can make me, when I try to maximize. Now the first is always at most a second, but they're equal if and only if the game admits an Nash equilibrium. And in this case, it can be also shown that the profiles are a Nash equilibrium if and only if they are max-min strategies, so strategies which attain max-min for those players. And the value of the equilibrium is the same for all the players. It's the max-min, min-max value. And also we prove the exchangeability. So as I said, the condition to be in equilibrium is basically the same as being the max-min for the respective players. So it's not dependent on the other player. Therefore, if you have x, y, and x prime, y prime, which are equilibrium, any combination of those will yield you an equilibrium, because a strategy can be independently of the other player's strategy, such either to be a max-min or not. So if xy and x prime y prime both are in equilibrium, both are Nash equilibria, then also x y prime and x prime y constitute Nash equilibrium. And another thing which we can define and say about those games is that the following: a pure strategy is called active if there is a max-min strategy of that player, which gives a non-zero probability, which gives a positive, strictly positive, in other words, probability to that strategy. So, in other words, a strategy is effective if it appears in the support of ace of some max-min strategy. So, it's somehow active. Now, another definition, a pure strategy is equalizing, and that definition is what we use. There are other definitions of this using the same term, so please notice that's what we use here on the slide. Pure strategy is equalizing if it achieves the best possible, so I is max min, against the other player's max min. So when the other player does what is best for her, given the expectation that, given the assumption that I will do the worst for her, the best I can get is my maximum value, and if there is a pure strategy that exactly attains this, it's called an equalizing strategy. And we prove that if strategy is active, it's always equalized. Okay, so that's something about zero-sum games. And then about the general game, we first proved that there exists a Nash equilibrium if a game has a compact and convex strategy set, a subset of a Euclidean space, which is the subset is compact and convex, and the functions, the utility functions, are continuous and what is called quasi-concave. Now, actually, the preferences are quasi-concave, but we always assume here that the utility functions are, the preferences are represented by the utility functions. And that is a sufficient condition for the existence of a Nash equilibrium. Now, of course, being a convex set means that it cannot be finite unless it's only one point, which is not interesting. Now, what about finite games? So a finite game does not have to have a Nash equilibrium. For example, matching pennies or rock, paper, scissors, they don't have an equilibrium. But a mixed extension of finite game does. A mixed extension is the game which is attained from any game, not necessarily finite, by defining the new strategies of a player, being all the distributions over her pure, original, we call pure, over her pure strategies. And the mixed extension defines utilities as the expectations over the player's utilities given those independent randomization of all the players. So the independent randomization of one strategies is a strategy, is a mixed strategy. And then we define as the expectation, that's how we define the utilities. That's a linear multilinear function. And the Nash proved that now here it's important that the game is finite. If the game is finite, then such a game, then the mixed extension of such a game always has a Nash equilibrium. So the game, we call it, has a mixed Nash equilibrium. That's the famous Nash theorem from 1951 and from 1951. And I also proved that a symmetric game always possesses a symmetric mixed Nash equilibrium. Okay. Now, another important solution concept is rationalizability. So we start with talking about mixed dominance. I mean, as I already said, that when we're talking about strategy, pure strategy being dominated, I can speak about the pure strategy being dominated by a mixed strategy, not only by pure. And that is because the process of iterative elimination of such pure strategy, pure strategies which are dominated strictly, here it's important, strictly dominated by pure strategy, always results in the same set of strategies. It's not true for weakly dominated strategies, it's true only for strictly dominated. And this set in which it results is also is equal to the set of all rationalizable strategies, and those can be defined as strategies which can be seen as the best responses to a belief about what the others do. When the belief assumes that others are rational, so whatever they do can be a best response to any belief of theirs, to what the others do, which also has to be a best response to any belief. So these beliefs don't have to match. It's not like an Nash equilibrium that we require that we actually have true beliefs, but simply all of those have to recursively be a best response to some belief which is itself a belief which itself assumes that the players are rational. So it's something which includes Nash equilibrium, because if something is a Nash or even a mixed Nash equilibrium, well, let's speak about pure. So if it's a Nash equilibrium, then it's the best response to an actual strategy, which is actually also a best response to the best responses. So a Nash equilibrium by that is immediately clear by definition rationalizable, but rationalizable strategies can be more than Nash equilibrium, but they also are practically more justified. So there is a good book about epistemic game theory by Pereira, who claims that in his opinion, indeed rationalizability strategy profiles, sometimes these are too big, strategy profiles, those strategy profiles, but they have the advantage that they are they are justified, because we assume only only rationality. We don't assume that you exactly know. We don't assume you are omniscient about the actions of the others. It's maybe too much to assume that you are perfectly rational, actually, but at least that's not as bad as assuming that you are even omniscient about what others do. So now there is this connection between the result of iterated elimination of strictly dominated strategies and rationalizable strategies. And also that a strictly dominant strategy is never rationalizable, because it can never be a best response to anything, in particular to anything which is itself a best response and so on. But a weakly dominant strategy can be even in a Nash equilibrium, and of course therefore rationalizable. So as I said, you can not remove weakly dominated strategies without running the danger of removing a strategy from a Nash equilibrium. And the next topic is the issue of security and stability. So the Nash equilibria, they are actually defined by the some, not any, but some possible rationale for stability, right? So you assume that nobody can deviate can deviate, and thereby strictly increase her utility. You cannot do that. That's the notion of stability. Now max-min, it can be defined not only for zero sum for any game, it can be defined for any game. It's a notion of security, so that you maximize what we get in the worst case. In the constant sum games, this is equivalent. However, this is not the case in general. In general, stability is, for example, any, and security is max-min. And it does not have to be the same, and so that's not the same. And now we saw examples. Another topic we also consider a bit more in depth is the topic of dominant strategies. So a strategy profile A excuse me. Okay, so I fixed this typo. Now, a weakly dominant strategy profile can be shown to always be a Nash equilibrium. Well, it's a best response by the definition of being weakly dominant. It also can be shown to be always a max-min vector. Again, to anything it's a max because it's weakly dominant. Now a strictly dominant profile, so a profile made of only strictly dominant strategies, if such exists, of course, it usually does not. A strictly dominant profile is the unique Nash equilibrium and the unique maximum vector. Another thing is that deleting a weakly dominant strategy does not change the player's max-min. A weakly dominated, it was weakly dominant, here is deleting a weakly dominated strategy. Because it's weakly dominated, it does not change your max-min, quite intuitively. It, however, can increase the max-min of others, but never decrease it. So now you have less actions towards others. So for them, it can only become better. And the next topic is efficient. So we already defined efficiency measures, which, as we said, depend on the way you define social welfare, the solution concept, and the concrete efficiency measure. In particular, we look usually at the efficiency measure price of anarchy and price of stability. And we look at usually at Nash equilibrium, but not only. And we look at the social welfare defined as the total social welfare, which is called also the utilitarian social welfare. So when you want to maximize what the totality gets. And we said that it's a very important topic. Both theoretically, people use much ingenuity, and there are many ways to find bounds on those efficiency measures, especially on price of anarchy. And practically, if you know that a game has, for example, only social optimum Nash equilibria, you know that there is no need to regulate it. If a game has both social optimum and also strictly suboptimum, you have a reason to at least hint the players so that they play the social optimum profile, the social optimum equilibrium. And if all the inefficient equilibria are inefficient, then it won't have regulating, because it's unreasonable to expect players to play something which is not the solution concept. But you may want to change the game. That's a question of mechanism design. That's beyond the scope of this course. And in the language of price of anarchy and stability, having only social optimum equilibrium. So when every equilibrium has social optimum, it means the price of anarchy, and of course also the stability then is 1. If some are optimum, some are not, it means the price of anarchy is strictly larger than 1, but the price of stability is 1. And if only equilibria can be only inefficient, it means that even the price of stability and of course the price of anarchy are strictly larger than 1. So that's important to know. And we in particular look at 4 important examples, classical examples. So we looked at network routing, when you need to route a certain amount of flow through a given network. We looked at network design, when you need to design a network, which means that every player has to choose a path between her sink and source, and you do it so that you won't have to pay much, because you can share some payments for an edge which is used by several paths. And then there was the scheduling game, which is just that the jobs choose to which machines to go, and the question is how to do it efficiently. And of course, you know many ways to measure how good the scheduling is, like make, span, and so on. So that's actually a very important, practically important example, of course. And the example of allocated resources based on what players say, how much they wanted, but when they have to pay for this thing. So it's kind of an auction. That was an example of resource allocation, when we assume allocation proportional to the bids, to how important the player claims that the resource is important for him. And mechanism design is often guided by efficiency measures. So when you want to often find a mechanism so that the game, the resulting game, will have good laws bound on the price of anarchy. Now, we also briefly mentioned and studied other solution concepts. So first, the strict Nash equilibrium, which is simply a specific case of a Nash equilibrium when a unilateral deviation not only cannot improve, but it has to strictly decrease the deviated utility. In particular, it's a Nash equilibrium. We also generalized Nash equilibria. Well, that was a simple generalization. We also looked at the systematic generalization of Nash equilibria as to how the players can randomize. So which strategies the player can choose. So we have already seen the just Nash equilibrium when we have just given strategies, which we call pure strategies. We also can talk about mixed Nash equilibria when the players can independently randomize between their own pure strategies. Now we also studied correlated Nash equilibria when the players have there is some event and there are some random variables on that event. That every player has her own random variable, so we have different knowledge but about the same event. So we have to randomize, and that can be correlated by this event. So that's called the correlated Nash equilibrium. And so every time we assume that the players do something when they cannot unilaterally strictly improve, but what they can do is bigger and bigger. So when they can randomize, it's bigger than just playing the pure strategy, and when they can randomize using some correlation, it's better. It's not better necessarily better, but it's bigger. The space of strategies is larger than the space of independent randomizations only, and therefore a best response which a player can achieve given the set of strategies of the others is gives her at least as good a utility as before, because the space of choice is bigger. And the last version we only looked at one tutorial was coarse correlated equilibrium, but we only briefly looked at it, which is when you can anyhow randomize between any correlated profile. So you don't have to use common strategy space based on which you get some knowledge, but you can just randomize however you want. Another way of generalizing Nash equilibria was that a normal Nash equilibrium, classic just Nash equilibrium, assumes that the profile is deviation proof with respect to the deviation of a single player. Now, what if players can coordinate and deviate in a group? So when we want to say that the profile is deviation proof with respect to deviation of any group up to size k, we call this equilibrium k strong, and when the size is at least the size of all the agents, we call it just strong. So that's a subset of the set of Nash equilibria, because the requirement here is that it's a deviation proof for the deviations of a coalition. Another way to generalize, that's not actually a generalization of Nash equilibria, that's just another solution which is related to modeling evolution, where strategies of population can give them different fitness, and a strategy which gives higher fitness results in the population growing, and being stable is a strategy which is never worse relatively to any other mutant strategy in that population. And such a strategy is called evolutionary stable. So they're just, of course, scratching the surface of a large part of game theory, which is called evolutionary game theory, which is used in biology and social sciences. So, of course, there are infinitely many possible solution concepts. We just have looked at some of the most important of them. So, to wrap up, we've been concentrating on strategic games. We studied various solution concepts and looked what we can say about those and about the efficiencies in various games.